So now at this point, the temperature becomes constant. And what you're noticing is that in the previous part, what you used to say was the temperature, sorry, the particles are using the energy to break the intermolecular forces of attraction. But here, the particles are still losing energy. But now what's happening is that the particles are coming closer together. Okay, particles are coming closer together. They're losing energy and they are coming closer together. Okay, so the forces of attractions are what happens. Forces of attraction increases, right? That's our idea. And then what you also know is that at this point, from point X to point Y, you have what? A gas plus liquid mixture. Okay, and particles still move, but they move more slowly compared to when they were moving in gases. So you see, and also they come in a some ordered manner, not that ordered, because even in liquid the order is not that regular. So we call this what? A slight disordered manner. And then from point Y to point Z, I mean, it's again the same idea that we have now done so many times. It's the same process. Exactly what was from W to X, exactly what follows from Y to Z. So what's now happening is that point Y, all of the gas has now been converted into a liquid. Okay, and now what happens? You're still cooling it. That means energy is being transferred out from the substance to the surrounding, and particles, they lose energy, right? Because you're sucking out energy. Particles lose energy, and losing energy means that they lose movement, yes, and then they lose kinetic energy. And if they lose kinetic energy, which means kinetic energy is decreasing, that means temperature is also decreasing. Okay, and that's why you see again a decreasing graph, which tells you that the temperature decreases after all the gas has been converted to a liquid. Okay, and if you even want, I can show you further explanation of this graph. So it's decreasing. Here you have a gas plus liquid mixture. At this point you have a liquid, and till this point you have a liquid, but you will go down, 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 and eventually you will reach a temperature where now this liquid has to convert to solid. And at that point this graph becomes like this again. So the process of going from a liquid to a solid, which is freezing, happens, and we have studied that before. And then the graph again goes like this. But you don't need to know that, because we are studying these in individual manners. So I think even till this part is what you actually need to know. Okay, I hope this is clear. And yeah, there are a few more concepts that I want you guys to know. And one of those concepts is evaporation. Some of you might know it. To people who don't, I'll just give you a quick explanation of what evaporation actually is. Now evaporation is simple. Basically the idea is when you're converting from a liquid to a gas, that thing is called boiling. Okay, that thing is called boiling. In this whole process we've been studying melting, right? We have studied melting. I think this was probably, yeah, melting, the first graph that we did. And then we studied freezing. Okay, then we studied boiling, which is this one. This is your boiling. And then we studied this one, which is, I mean, what do you call going from a gas to a liquid? I think that was condensation, I guess. I forgot the name, maybe. I might be wrong here, okay? Even I can forget. Anyways, now evaporation is basically a process. You see, whenever boiling is happening, let's say you have this beaker and you have this water inside this beaker, and you're actually heating it. Okay, you're actually heating it. So what you should know is that, imagine a classroom, right? If I ask you that you have a classroom, and in that classroom you have 30 students and all of them are standing. So I want to know, in this particular classroom, and there is your door. Okay, there is your door. I mean, this is the door. Okay, this is the door, and you've got 30 students standing inside the classroom. I wonder, if I ask you who can leave this classroom the fastest one, who is the fastest one who can leave this classroom, you'll say the person who are standing close to the door, right? They will be the first one, or they will be the person who can easily leave the classroom at the earliest, right? That is the process of evaporation also, because what happens is that you have got liquid, so all of the there are liquid particles, right? There are liquid particles like this. Some particles are at the bottom, some at the top, some at the, you know, at the middle. So the middle and the bottom particles, they are surrounded by each other, but the top particles, they have middle particles at the bottom, and at the top they have nothing, right? They are contact, they are at the surface, they don't have anything at the top, they only have air at the top. So what really happens is that from particles that are here in the water, or they're in the liquid, these particles that are at the surface level, they have a lot of energy, and because they don't have anything stopping them, just like these guys are standing near to the door, what they do is that they come in contact with the air and they evaporate. But what you also need to know that this evaporation happens at temperature lower than the boiling point. So for example, if you're boiling out water, water has a boiling point of 100 degrees centigrade, but this evaporation is actually going to happen at temperatures lower to that, and it can be any temperature, maybe 60, 65, 70, 85. It just means that the particles that are at the surface, right, they have enough energy, they can evaporate, they can fly off from this liquid and, enjoy in the air. Okay, that is your idea about evaporation. It's just that what particles can leave the earliest without reaching the boiling point. Okay, that is a one idea. The next idea is liquefying gases. Okay, and you might ask, what does that mean? I'll tell you. That means is that we have a way through which we can, store gases in the form of liquids. And this is actually a very common thing that happens, right? I'll tell you how, sorry. If you have visited a hospital or anything, you'll always see that you have oxygen in tanks, right? You have a very big tank, and they say that in these tanks you have got what? You've got oxygen. Do you think that that is oxygen in the form of gas? No, this oxygen is actually liquid oxygen. And the question is, why do they store oxygen as a liquid? Now here's the concept. Gases have particles very far apart. Okay, very far apart. So if I were to put them in a container like this, the particles are very far apart, right? Very, very far apart. While meanwhile, let's say this is 30 centimeter cube of gas. I don't know if even the unit is right, but anyways, I'm just telling you a rough idea. That, let's say this is 30 centimeter cube of gas, right? And it is occupying this much space. Because why? Because the particles are so further apart. But what happens is that when I convert this liquid oxygen, this 30 centimeter cube of, sorry, gaseous oxygen into liquid oxygens, now liquids have particles much closer. Okay, now in liquid form, this is what you have in 30 centimeter cube of oxygen. So what you actually notice is that in liquid form, gases occupy much lesser space than they occupy in the form of a gas. Why? Because gases have their particles very far apart. You see how far these particles are. In liquids, that's not the case. The particles are slightly closer together or much closer together compared to gases. That's why we liquefy gases. That's why we put gases in the form of liquids, so that we can store large amounts of gases in liquid form, but so that it also utilizes much lesser space. That is our idea. That's why we liquefy gases. That's why oxygen that you see in hospitals, by the way, these are in liquid forms, because in liquid you can store much more oxygen in the same space than you can do it in the form of gaseous in the same space. It's all about the space that they occupy. That's why we use them in terms of what? In terms of liquid. Okay, I hope this idea is clear.